Now let's go to the finite dimensional. Let's specialize this statement to a finite dimensional function space. All right. So in a finite dimensional function space, what's special is that f can be represented as a linear combination of basis vectors, right? So f can be represented as let's say I goes from 1 to n of ai times hi, where h1, hn they are the basis. They're the basis. Okay. And also, when I'm saying that the distance, the vector from my pen to the blackboard has to be orthogonal to any function, any vector in the blackboard, I actually only need to be orthogonal to a basis in the blackboard, right? So if you draw an axis, this blackboard is two-dimensional, so if I have two independent vectors to test my orthogonality, then I'm orthogonal to the whole blackboard, right? So what I'm saying is that if hi inner product with f0 minus this, let me use j here, ai times hi is equal to 0 for any j, then this should be true for any df, right? Because any df can be represented as a linear combination of these hj's. So if all of these are 0, then a linear combination of these zeros should still be 0, and I have this statement, right? Okay. So then this step simultaneously reduces the problem of finding f to a problem of finding n numbers. It also reduces this equality from infinitely many equalities, right? Because this has to be true for any df, into n equalities. Right, so this problem is an infinite dimensional. It's basically finding an f within the infinite set, right? This is finding f in an infinite set, right? To satisfy infinitely many equations. But because of the linearity of the space and the existence of a finite basis, we can reduce that equation into this, which is finding n numbers to satisfy n equations, which is something we know how to do, right? The n numbers are these a's, the n equations are one equation for each hj. Yes? You mean here? It's the basis. It's the basis. I'm sorry. I'm sorry. It's the basis. Sorry for my bad handwriting. Right? Do we? Any other questions? Okay. So let's actually list out what these n equations are, using this using the property of the inner product. So these equations are hj f0 minus summation again, linearity of the inner product. We can pull the summation out of this inner product. We can also pull the multiplication by AI out of this inner product. All right. So this is equivalent to this. Can somebody see this is a matrix equation? AX equal to B. All right. So this is actually A times X equal to B, where my X is this A's, A1, AN. Okay. My B is equal to this, H1, F0, H2, F0, HN, F0. Now what is my A? My A is an n by n matrix comprised of these pairwise inner products of the basis functions. Right, so the first element would be H1, H1, and the last one would be H1, HN. And interestingly, this is HN, H1. This is also a symmetric, right, matrix, HN, HN. All right, so what I need to do to accomplish this is I need to perform the inner products. I need to look at whatever function I draw. I need to compute the inner products of this function with my h's, right? I need to compute bi, which is equal to integration over whatever domain I have, f0 times hi dx. I need to perform this integral numerically, and then I need to compute aij is equal to the same integral hi hj dx. So once I computed this, I solve ax equal to b. I get the linear combination coefficients, and I use this to get my f equal to the linear combination with these coefficients and the basis function.